So in part 1, I have covered till multi-level. So these two topics, multiprocessor and real time, I have covered these two topics in unit 1 lecture. So today I'm going to cover all the topics of 4.5, that is deadlock system model, principal necessary conditions, and mutual exclusion and critical region. So here is my part 2 lecture of unit 4 module. Alright, so topic is deadlock. In an OS, a deadlock occurs when a process or thread enters a waiting state because a requested system resource is held by another waiting process, which in turn is waiting for another resource held by another waiting process. Now let us understand this concept with the help of simple example. Let us consider person A has a marker and person B has whiteboard. So in order to conduct a class, person A needs whiteboard and person B needs marker. So if both of them want to perform the same activity at the same time, then they cannot do so because both of them entered into the state of deadlock. So here in figure, it actually represents the deadlock. We have two processes, process 1 and process 2. Process 1 is actually demanding resource 2, which is held by process 2, and process 2 at the same time demanding resource 1, which is held by process 1. So in this case, both of these processes cannot execute further because they entered into the state of deadlock. So this is overall the conception of deadlock. Now next is deadlock necessary conditions. Previously we have seen the concept of deadlock, so now we are focusing on the conditions for what reason deadlock occurs. Alright, see, if two persons have any conflict, it's necessary to understand the reason of conflict in order to get the solution, right? So let us see the conditions where deadlock occurs. So first one is mutual exclusion. There should be a resource that can only be held by one process at a time. Now let us understand with the help of example, right? Now you are watching my video lectures, right? At the same time, other viewers may also watch these video lectures, right? Is it necessary that others cannot watch this video lecture because you are watching? Answer is no, because the resource is shareable. Now let me consider another scenario. I left 2000 rupees in public space. Now is there any possibilities to get back that 2000 rupees? Answer is no. Why? Because everybody wants to use that resource. Ultimately everybody wants money. Now this is not shareable resource, but everybody wants it. So this is a problem. So this is what mutual exclusion says. Now next is hold and wait. A process can hold multiple resources and still request more resources from other processes which are holding them. Again, let me explain with some examples. Suppose you are going to some friend functions, right? Now you want some food. For that you need some plate and spoon. But at a point of time there is no spoon. Now you will hold the plate which is available, right? Because if you don't, others may grab that plate. Okay. So in this story, we have seen that even though you are not eating, you are holding plate. So this is what exactly hold and wait conditions are. Next is no preemption. A resource cannot be preempted from a process by force. So again with same example, you were left with plate and no spoons, right? So in that function, you have seen somebody is having food with spoon, right? Now, can you forcefully take that spoon and eat your food? Answer is no, you cannot do so. So this is what no preemption conditions are. And yes, no preemption means no other process can be taken into consideration until the executing process is completed. Now next is circular wait. See, we have three processes, P1, P2 and P3. So all these processes which we have discussed earlier, all the conditions is present in this scenario. So there is mutual exclusion, there is hold and wait, and there is no preemption. But there is, in this condition, there is no deadlock. So if I say P3 is waiting for P1. So in this case, now it occurs a major deadlock. So this is nothing but it is functioning in a circular wait. So let us see what circular wait says. A process is waiting for a resource held by the second process, which is waiting for the resource held by the third process, and so on, till the last process is waiting for a resource held by the first process. So this forms a circular chain. So this is what circular wait. By the term circular means it has to form a circuit. So this condition is very important in order to occur the deadlock. So these are the deadlock necessary conditions. To the next slide. First one is race condition. When order of execution can change the result, the condition can be termed as race condition. So now let us take an example with this small piece of code, how this code will execute in different scenario. So now we'll check in different scenario with the help of this small piece of code. So firstly I'm taking systematic execution, how it will react. So we have two processes, P1 and P2. So both the processes P1 and P2 will execute this small piece of code, and the value we will assume for A as 10, let us say. So P1 gets into the piece of code, and it will first read the values of A. R of A means read the values of A. It will read 10, and after that it will go to the next line of code. It will increment the values of A, which will become 11. And after that, after incrementing, it will update the values of A. That means right of A means it will update the values of A, becomes 11. So in the case of sequential execution or systematic execution, P1, that is process 1, is getting resultant as 11 after execution of this small piece of program. Similarly P2, now P2 will run the whole program. Firstly it will read the value of A is now 11. So it will read the value 11, and then it will increment. Next line it will go to next line, and then it will increment. So increment the values of 11 as 12, since A is equals to A plus 1 means incrementing by 1 the existing value. So that means it will increment the value 12. After incrementing the value 12, it will update right W of A means right of A, which will update the values of 11 by 12. So process P2 is getting value 12 after execution of this program. So now we'll see mixed fashion execution. So mixed fashion execution is nothing but we can context switch in between the code. So context switching is nothing but if P1 entered into the program and start its execution, at the same time P2 can also request for the same program and start its execution. So this can be done with the help of concept known as context switching. So we have already discussed the conception of preemption. So this is nothing but it is also known as preemption. So again the same thing, we are assuming the same value of A is equals to 10. So in mixed fashion, again the same thing, we have two processes P1 and P2. So let us see, first P1 enters into the program and start its execution. So first P1 read the values of A. So it will read the values of A as 10. Again we'll context switch in between these two line of code, and then we'll give a chance to the P2. So P2 enters, and then P2 read the value as 10. Again we'll context switch, P1 increment the values as 11, as A is equals to A plus 1 is there. Again we'll context switch, and then we'll give a chance to P2. So now P2 enters into the program. It has already read the value 10, and it will go to the next line of code which says that A is equals to A plus 1. So again it will make the value as 11. Again we'll context switch, again we'll give a chance to P1. It has already incremented the values as 11. Now it will now it will update the value, that is W of A. So updating values of A is nothing but it has already updated, that is 11. So 11 will be updated in P1 case. Again we'll context switch, and again we'll give a chance to the P2. So it has already incremented this line of code, it has already executed this line of code. Now it will move to the next line of code, which says that W of A, which means updating the values of A. So values of A is updated by 11. So again in P2 we are getting the same results. So these are the resultant which we have gained from two scenarios. So in first case we are getting different result, and in the second case we are getting the same result. So this is what the condition arise, we can term it as race condition. Now next is critical region, the area in execution of process where shared resource is accessible. So we have already learned what is shareable resource. So in a program, it might have some section of code which is shared by all the processes. So that particular area which is used by all the processes is known as shareable resource, and that shareable resource area is known as critical region. So next is criteria to solve critical section problem. So earlier we have seen that whenever we talk about shareable resources, so there was a problem, right? So in order to solve those kind of problem, we have criteria. So criteria to solve problem is mutual exclusion, progress, and bounded wait. Where mutual exclusion is nothing but each process execute one time a resource. So if process P1 is executing a shareable resource, process P2 cannot demand for the same resources. So that is mutual exclusion. Next is progress. Only those process should compete or should be in the race to enter in a critical section, those who actually wants to do. Okay. So next is bounded wait. So bounded wait is nothing but after a specific time a process has to bound or has to get chance to go to the critical section. So that has to be maintained. So these are the critical section problem criteria. So here is questions for you all. What you have understood from this lecture, please answer yourself and make a note out of it. And these are my resources that I have used while preparing my slide. Lastly, thank you all for watching my lecture.